Hi, I want to talk about the oscillating system having a spring hooked up to a mass oscillating along a frictionless horizontal plane. Now, for all simple harmonic oscillators, you need a system that starts in equilibrium. It needs to be a stable equilibrium, so there needs to be some restoring force that is always going to be taking you back towards equilibrium. And that's exactly what the spring force does. If you compress a spring, it pushes back. If you stretch a spring, it pulls back towards equilibrium. So if we take a look at a force picture for this object, if we just pull it out some distance, we'd have a spring force pulling opposite the direction that we have, and as long as this is frictionless, we won't need to worry about the y components. So Newton's second law says our acceleration is the sum of the forces over the mass. That's just going to be our spring force divided by our mass. So our acceleration would be equal to the spring constant times our stretch x away from equilibrium divided by our mass in the negative x direction, negative I hat. Well, acceleration is a derivative. It's the second derivative of position. So leaving the direction aside, if we take a look, we need to have a position that as a function of time can solve the relationship that its second derivative is minus some constants times that original value. And two functions come to mind that have a second derivative that's minus the function itself. And those are sines and cosines. And we're going to use the cosine function. So let's guess that x can be described as a function of time where x of t is equal to a constant a times the cosine of a quantity omega t plus phi, where t is the time that's elapsed and omega is a quantity measured in radians per second and phi is an angle in radians, just so that we have the freedom to start our trig function wherever it would happen to be when we start looking at this oscillation. Well, if I take this equation and plug it in, I'd have minus the spring constant over the mass times a cosine of the quantity omega t plus phi. If I take two derivatives, the derivative of cosine gives me minus the sine, but then using the chain rule, I need to take the derivative of what's inside. And the derivative of omega t with respect to t is going to give me omega. I then take a second derivative, I get a second factor of omega from the chain rule, and the derivative of minus the sine is minus the cosine. So I would have minus this value a times this value omega squared times the cosine of the quantity omega t plus phi. Now we can play the match game. Both have a negative sign in front. So that negative sign can cancel out. Both have an amplitude A in front. A for amplitude, that's why we chose that letter. That can cancel out. Both have this exact same oscillating function, cosine of omega t plus phi. Those can cancel out. And this relationship works as long as this value omega squared is equal to the spring constant divided by the mass from our Newton's second law equation. And this is something you see with every simple harmonic oscillator. All simple harmonic oscillators have a quantity that we call the natural frequency omega that's set by applying Newton's second law to the problem. So for the spring mass, our natural frequency for an undamped spring mass system mounted horizontally is going to be the square root of the spring constant divided by the mass. Thanks for watching.